2 or power 3, when you make the conversion, make sure your unit factor also has that power in it. So that's where a lot of calculations sometimes go wrong. Key to these calculations, which are really basic and you really need to move on, is practice. Okay, so please practice, do the homework in a diligent way, take it seriously. It's for your own good. Okay? Not because I want you to do it, but because you want to do it to yourself. You educate yourself. That's why we're here. You don't have to please me once again. Please don't make me happy. Do not make me happy. Make yourself happy. All right. Atoms, yes. Oh, I haven't even looked up on the chemistry Nobel Prize. Yeah, I think the one was issued today. Yeah. All right, great. Yeah, let's all look that up after class. I actually haven't seen it. I was so busy on things, but yeah, today was the release of the Nobel Prize. Thank you for pointing that out. Okay, now, we already have seen in the first lecture, and this is something that we all know about, that matter is composed of atoms. In chemical terms, atoms are the building blocks of nature. Okay, so, and this slide just reiterates that point. We like to conceptualize the world around us in terms of small particles that build up something bigger. Okay? This is, of course, little tiny objects that are small things that make something bigger. Here is basically, you go down to a very, very small scale of what we see with special instrumentation. I pointed out a week ago. These little tiny blobs are individual atoms or compounds like small molecules that can be sensed with these special instruments like STM microscopes. Okay, so these particles, these little objects are really there, not some kind of creation by scientists, okay, which is just conceptual. This is real stuff, and they make up matter around us. Now, this is a concept that really goes back all the way to Democritus, as you've seen. Here he is again. He says, matter and space are not infinitely divisible. At some point, you cannot divide up anymore. You are going to hit a fundamental particle. And this fundamental particle is the fundamental building block of matter around us. And Democritus was very close in his description of matter, at least the way we understand matter. Okay? But this is not something that is easy to conceptualize. We all, again, we know this because of years of human history, but after Democritus, Aristotle, as we know, said, I don't believe that. All right? So he went back to a system that interprets matter in terms of different kinds of elements, like fire, or air, and so forth. Okay? So currently, we don't like to use such descriptions because it doesn't really fit a lot of experiments, as we know. So, years after Aristotle, people like John Dalton realized that the Democritus description was a much better way to explain the world around us. Much more consistent and with much more predictive power than the way in which Aristotle envisioned it. Okay? He says, I think Democritus is right. And John Dalton thought about this even more. And he says, I think we should think about matter in the following way. He says, matter is composed of elements, and those elements are extremely small particles, which I call atoms. Okay, an atom is a particle, and an element is a kind of atom. So there are different elements, which means there are different kinds of atoms. Now, all the atoms of the same element, so all the atoms that are the same kind, really are the same kind. They are no different. Okay? They cannot be distinguished. They have no different features. They are all identical. So whether you have 1, 2, 3, 4, 5, 6, 7, 8, 10, or a gazillion, they all are exactly the same. Okay? Yes?
Not the isotopes.
Well, we'll talk about it in a moment. Yes, talk about isotopes in a moment. Okay, so how can we think about it? We have atoms of element X, which have a certain kind of characteristic, but all of them are the same. Okay? So this one and this one cannot be discriminated from each other in terms of their properties, other than location. Okay? This is another element. So these are atoms of another element, and they're kind of like conveniently drawn a little bigger in a different color. But the point is here that they are different elements. The atoms here are all identical, but they're different from the atoms here because they're different elements. Okay? Okay, so that is an important realization. Then Mr. Dalton says compounds are composed of more than one element. So I can combine elements or atoms together. They can be of the same kind, they can be of different kinds, it doesn't matter. And I can make compounds in this way. So compounds are particles that have more than one atom in them. In this case, this looks a lot like the water molecule. Let's think of these balls as being oxygen atoms, atoms of the element oxygen, atoms of the element hydrogen. They can form a water molecule, which has one oxygen atom and two hydrogen atoms. Okay, so this is the basics of thinking about matter. Okay, so then Dalton continues, and he says, in any compound, the number of atoms of any two of the elements present is either an integer or a simple fraction. What that means is that an atom is an atom, cannot be split. It's either there or not. That means it's either 0, which means it's not there, or it's there, which is 1. Okay? So, carbon monoxide has one carbon atom and one oxygen atom. Not half an oxygen atom or a quarter oxygen atom. There's one. Okay? 1 is the lowest number you can have. The ratio between the two, therefore, oxygen over carbon is 1 to 1. The outcome of that is an integer or a simple fraction. Another example, carbon dioxide. 2 oxygen atoms, 1 carbon, so 2 oxygens, 1 carbon, 2 to 1. Again, the ratio between these elements is an integer or a simple fraction. Point is, atoms are not divisible. Okay, so they're either there or not. There's one here, one there, not half or a quarter atom in a molecule. And then lastly, and very importantly, a chemical reaction involves only the separation, combination, or rearrangement of these atoms. It does not result in the creation nor the destruction of these particles. Okay? So the atoms themselves are not created or destructed in the process. Chemical reaction is just a rearrangement of the available atoms. You don't take any atoms away, or you add any atoms to it. The total remains the same. You just put them in different places, and you form different molecules. So we'll talk about this extensively in classes. Okay, so the atom is an important concept and fundamental in chemistry. So what is the atom made out of? Well, the atom is made out of electrons, protons, and neutrons. And so we have to look at these particles very briefly in order to appreciate what they do and where they are in the atom. Let's start with the electron. The electron is basically symbolized by a letter E, and you can put a minus sign behind it because the charge is negative. Now, what does it mean, negative charge? It means basically that the particle has a charge. The negative is just by convention. I could as well call this a positive charge. Okay? But we call it a negative charge, which means the opposite charge of this is positive. But it's interesting to think about. This is just by convention. I could as well have decided that the charge of electron is positive, and then the charge of a proton will be negative. Okay? That's not how we did it. We said the electron has a negative charge. Okay? Now, the existence of electrons can be proven. And here's one way to do it. You can generate electrons in this fashion here. There's a cathode and anode. This contraption here generates electrons. Okay? And And then you can actually send them through this field, this magnetic field. And electrons have a very peculiar property. They have a spin quantum number, which is either half or minus half. And so what you get basically is you get two different spots, A and C, of the electrons that are having divergent paths. There are two possibilities. Either electrons are not scattered, or they're scattered in two ways, and these two ways correspond to a quantum number or an electron spin up or down. Okay? So this is a kind of a pretty complex measurement, and we'll get back to this, what this means, electron spin, but the fact that you can prove the particle has an electron spin proves that an electron exists. Okay? It also gives information about the charge, that this particle really has a charge, and that actually explains why it has a magnetic quantum number. And the charge is, like I said, by convention, a minus sign. The value is expressed in Coulomb, and that's a capital C. Okay? This is the value of the charge of the electron, 1.6022 times 10 to the minus 19 Coulomb. It's a very small number, it's a very small charge, because the charge of the electron is very little. It also has a mass. The mass of the electron is also very tiny, expressed in grams. Now be careful here, because sometimes in some tables the mass is expressed in kilograms, in other tables in terms of grams. The difference is a factor of 10 to the third. Okay, so please look carefully in what unit the value is expressed. In this case, it is in terms of grams. And in terms of grams, it is 9.1 times 10 to the minus 28. 10 to the minus 28. Very little. One tiny sugar cube, small sugar cube, weighs approximately a gram. And so this thing, one electron, is 10 to the minus 28 times lighter. Okay, so this is a humongously small number, very small number. Therefore, the mass of the electron is very, very tiny. Okay, let's move to the proton, which is also a charged particle. So we indicate that by this plus sign. You can prove their existence, and there's a, there has been a wonderful history in proving the existence of fundamental particles. And here's one for the proton. You can create so-called alpha particles, which basically are helium nuclei, and you can send them through a piece of gold foil. And this is basically how researchers envision that. If the atoms of the gold would be basically empty space, then these particles sent through would simply just go straight through. They wouldn't change their path. Okay? So the alpha particle is a positive particle. When it hits one of these nuclei, then it can actually change path. All right? And the charge of the nucleus is an indication of how much and how far these alpha particles can scatter and change their path. So you don't have to worry about the details. But the fact, indeed, that you get a particular pattern behind this gold foil indicates that the alpha particles are scattering off positive particles in the gold atoms. And the positive particles are identified as protons. Okay? All right, this is how people prove that these things existed. For us, what we have to realize is that it has a positive charge, that basically means an opposite charge relative to the electron. There's a plus sign. The value is the same. It's the same value, different sign. The value also is 1.6 times 10 to the minus 19 Coulomb. It also has a mass. The mass is again super tiny, 1.67 times 10 to the minus 24 grams. And that is, if you remember the value of the previous slide for the electron, that is more than the mass of the electron. In fact, it's almost 2,000 times heavier than the electron. So the mass of the proton is more than the mass of an electron, while the value of the charge is the same. Okay? The value of the charge is the same, the sign is different, and the mass is different. Okay, there's another particle Actually, this is the way in which people in the physics department like to think about a proton. It is actually composed of quarks, 2 up quarks and 1 down quark. We don't really have to bother about this. This is very interesting, but for us chemists, the existence of quarks is irrelevant for explaining chemical phenomena. Okay? So we'll leave that to the physicist. The neutron is our final particle of interest. Not Jimmy, but this thing here is where people can generate neutron beams and study the properties of neutrons. Very interesting. And they are an essential component of atoms. The charge, interestingly, is 0. So this is a neutral particle, hence the name neutron. It does not have a charge like a proton or electron. It does have a mass, so it's a real particle. It has a mass. And the mass is 1.67, almost the same as the mass of a proton, but a little bit different. A little tiny bit different. 1.67 times 10 to the minus 24. For all intents and purposes, the mass of a proton and a neutron is approximately the same. Okay, so electron, proton, neutron are the ingredients of an atom. And again, the neutron can be thought of as composed of 3 quarks, 1 up quark, and 2 down quarks in this case. All right, now, how does it work then? This is the way in which we understand atoms are built up. They have a nucleus, and the nucleus is composed of neutrons and protons together. They form a nucleus, and the nucleus is held together by a particular force. It's called a nuclear force. This force is very prominent on length scales that are relevant to an atom. This nuclear force is not relevant to length scales in which we live. So we rarely experience a nuclear force. Gravitational forces and electromagnetic forces are the forces we have to deal with. But on the length scales of atoms, the nuclear force becomes very important, and this nuclear force holds together the protons and neutrons. So, as you can see, the neutrons are neutral, the protons are positive, so overall, the nucleus has a positive charge, because it has positive protons in it. Now, the diameter of the nucleus is rather small. We have actual numbers for these things. Okay? The hydrogen nucleus, which is 1 proton. The hydrogen nucleus is 1 proton, 0 neutrons, just 1 proton, 1 fundamental particle. That is the hydrogen nucleus. The approximate diameter of that thing is 1.7 times 10 to the minus 15 meters, or 1.75 femtometers. That is the diameter of a hydrogen nucleus. A very small number. A femtometer is a very small number. Yes?
What is the force that attracts the electrons?
Can you say that one more time, please?
What is the force that attracts the electrons to the nucleus?
Oh, well, the main force that keeps the electrons close to the nucleus is the electromagnetic force. The electromagnetic force. So basically, the electron is negatively charged, the nucleus is positively charged, and that is the main attraction between the nucleus and the electrons. It keeps the electrons close to the nucleus. Okay, so this is the hydrogen nucleus, very small. A uranium nucleus, which is much larger, looks like this. Uranium nucleus has 92 protons, okay, so the hydrogen has only 1. Okay? Uranium has 92 protons, and in addition, it has 146 neutrons. And that's a much bigger unit, much bigger particle. Its diameter is almost 10 times larger, 15 femtometers. Okay? So again, a very small number. So the nucleus is tiny. Now, how big is the nucleus compared to the atom overall? So this is a good way to think about it. Here's the nucleus, and its size is on the order of a femtometer, as we just have seen. Okay? The femtometer is approximately 10 to the minus 13 centimeters. Okay? So 10 to the minus 13 centimeters equals 1 femtometer. So that's the size of the nucleus, and then this kind of haze around it is the location where the electrons float around. So the electrons can be here in this area, okay, that is shaded here, and the extent, the distance with which they can move away from the nucleus is much larger than the size of the nucleus. Okay, so in this case you can see 10 to the minus 8. The difference is pretty prominent. And I'll give you an example in a few moments to appreciate the size of the nucleus compared to the size of the atom as a whole. Here in this table we see very quickly summarized those fundamental particles, the electrons that are basically somewhere around the nucleus, and then the nucleus itself composed of protons and neutrons. The mass of the atom is largely determined by the protons and neutrons. The mass of the electrons is very tiny compared to them. So the electrons rarely contribute to the mass of an atom. It is the protons and neutrons that define the mass of the atom. Electron is charged -1, proton +2, and the neutron is neutral. Okay, so let's look at this one more time in terms of numbers. Okay, so the diameter of the hydrogen atom is a proton nucleus and an electron. One electron, one proton, plus minus, overall neutral. That constitutes one hydrogen atom. Okay, so in the middle there is a nucleus, which is a proton, and around it somewhere is swerving an electron. So the orbit of the electron, the extent of the orbit, is 5 times 10 to the minus 11 in terms of the diameter. Okay? That's 50 picometers, about 50 picometers. That is the extent of where the electron can be relative to the nucleus. Okay? So remember the diameter of the nucleus itself is 1.7 femtometers. So this is a picometer, 50 picometers. This is femtometers. Pico is 10 to the minus 12, femto 10 to the minus 15, which means a lot smaller. The nucleus is a lot smaller than the total size of the atom. So let's do a quick calculation with that. So the ratio between these two numbers, which is the size of the nucleus relative to the size of the atom itself, is a small number, 3.5 times 10 to the minus 5. Okay, so that means that the size of the nucleus is just a fraction of the total. If we do a very precise calculation, we can divide the diameter in half, which means we have the radius. Okay? The radius is this much smaller. Okay? And that means that if you take the cube of that, you end up with a difference, or a ratio between the volume of an atom and the volume of a nucleus, which is very, very small. Okay, so 10 to the minus 15. So that is an enormous difference. Okay, the nucleus is a lot smaller than the atom itself. That's basically what it says. And just to kind of reiterate that, if you think of the atom as a big football stadium, and you put a little tiny marble in the middle, then you can say that the nucleus to an atom is what the marble is to the football stadium. Okay? So in the middle you have a tiny little marble, that will be a nucleus. The orbit, the size of the orbit of the electron is kind of symbolized here by the extent of the football stadium. The electron can be anywhere in the stadium, while the nucleus remains there in the middle. Right? So that basically means the atom is mostly empty space. Mostly empty space. What is empty space? It's nothing. There is no stuff there. Okay? No air or whatever. Just nothing. Okay. Now we're going to hit the topic of isotopes. Already brought up here. What is that? Okay, so let's look at this particular nucleus. This is a nucleus which is the sodium nucleus. The sodium nucleus has 11 protons. Okay? 11 protons. In fact, the number 11 defines that this atom is a sodium atom. It is the atomic number. Every atom with atomic number 11, which means it has 11 protons, is a sodium atom. This atom also has 12 neutrons. 12 neutrons. Okay, so 11 protons, 12 neutrons, that is going to be the nucleus. If you add these guys up, you get 23. 23. That is this number right here. So this number right here is the sum of the protons and neutrons. Okay, now look at this guy here. Its little brother. It's also a sodium atom. Why? Because it has atomic number 11. It has 11 protons. But lo and behold, it has 13 electrons. Sorry, neutrons. Thank you very much. It has 13 neutrons. And that means that, I mean, I would ask the question, does that mean that it's still a sodium atom or is it something else? It's still sodium, because sodium is basically 11 protons, but it is a different kind of sodium atom. So it's true indeed, you can have different kinds of atoms of the same element. Okay, so you can have different isotopes. So the way to write this is 24 is the sum of the neutrons and protons. This one is still 11. So these two sodium atoms are each other's isotope. Okay? Both have 11 electrons. Why? Because an atom overall is neutral. They both have 11 protons. That means they have both 11 electrons. Only difference between these guys is that this guy has one more neutron and therefore is heavier. Okay, so this is a heavier isotope relative to this guy. So their masses are different. They can have different masses. Same characteristics. Otherwise, but their masses are different. Here's a list of isotopes. Most elements have multiple isotopes, some of which are very abundant and others are very scarce. Okay? For instance, there's more, actually, there's two, but there's more than 2 isotopes of hydrogen. The most prominent ones are hydrogen 1. The abundance is 99.9%. And then a tiny fraction is deuterium, which is hydrogen 2. 2 meaning it has a neutron and a proton. This one only has a proton. Lithium, lithium 6, lithium 7, the difference between them is 1 neutron. They do have the same amount of protons, but they have different amounts of neutrons. You can look at the abundances here. Lithium 7 is the most abundant lithium atom. Boron, there's 2 listed here. There's actually more in reality. They are the same. They have the same number of protons, but different number of neutrons. They differ by 1. Carbon, carbon 12, carbon 13. Oxygen, there's 3 listed here. Oxygen 16, 17, 18. They are all oxygen atoms, but they have different amounts of neutrons. Their abundances are also very different. Look, this guy here is the most abundant. The other ones are very rare. And so forth. So, in summary, most elements have multiple isotopes. Usually there's 1 or 2 isotopes that are very abundant, the rest is very rare, or has a very short lifetime. They fall apart. Okay, now let's look at this a little closer. If you look at the periodic table, you will see something like this. 6 above this symbol, which is carbon. This is the symbol for carbon. And then below it, another number. That is the number of protons, or the atomic number. So the atomic number corresponds to the number of protons of the element. That is the average atomic mass. Tells you something about the atomic mass. But this word is, has a different color than this, which means this is important. This is the average atomic mass. What does that mean? We're going to talk about it right now. Okay, so this P doesn't belong here. Okay? The isotope notation is the following. If you have C12, there should be a 6 below it. That means there's 6 protons. 12 is the sum of protons and neutrons. So we subtract 6 from this, you get 6 neutrons. So carbon 12 has 6 neutrons. The relative abundance of that is pretty high. So most of the carbon atoms are actually carbon C12. Carbon C13, 13 minus 6, that means 13 is the sum of neutrons and protons. You subtract the total amount of protons, which you are left with, is the number of neutrons. It has 7 neutrons. Its abundance is much less, it is 1.1. If you add these guys up, you get almost 100%. So carbon C12 and C13 together basically comprise all of carbon, approximately. A few more tiny isotopes, but they are of no significance. So what is this average atomic mass? It is the atomic mass of both elements given their abundances. You have a question?
So we don't include carbon 14 because it's not much.
Carbon 14, its abundance is extremely little and has no impact on the average atomic mass. So that's why we'll leave it out of the discussion. Okay, so let's look at this atomic mass a little closer. What is the unit of atomic mass? Well, you can express it in grams if you want, but there's a different unit that is easier to work with. And that is simply called the atomic mass unit, or AMU. AMU. This is the definition of AMU. 1 AMU equals the mass of one C12 atom divided by 12. That's very interesting. That is the definition. Why this and not something else? Well, we could approach something else. But this is just the definition we come up with. So this unit is just a convention. It's not rooted in anything fundamental. We have to design a unit. We decide to do it in this way. 1 AMU is the mass of one atom of carbon 12 divided by number 12. That's it. So, then, what is the atomic mass of carbon C12? Well, you can see it here. The mass of carbon C12 is, put this 12 to the other side, is 12 AMU. Okay, so one carbon C12 atom equals 12 AMU. 12 atomic mass units. That's our convention. That's our convention that we will work with. Okay, so, but what is then the mass of other atoms? Okay, for instance, what is the mass of carbon 13? Is that just 13 AMU? The answer is not exactly. So let's look at that. The mass of carbon C12 equals 12 AMU. We just decided that. What is the mass of carbon C13? Well, that equals the mass of carbon C13 divided by the mass of carbon 12 times 12 AMU. That is the definition of the mass of other atoms. So, you take the mass of one of these atoms, you divide it by the mass of carbon C12, and then multiply it by 12 AMU. That is the definition of the mass of other atoms than carbon C12. Now, why do you do it in that way? The reason is because this number here can be determined experimentally relatively easily, because it's a ratio. Okay? So I can have the ratio, the relative mass of one thing to another thing. I have C12 here, I have C13 here. I don't have to determine the absolute numbers, only the ratio of these. That's something I can relatively easily do. But that number follows from experiment and is somewhat easily accessible. This is why we have this system in place. Okay, so this number is not exactly 1, as you can see. Okay, it's 1.08. If you multiply it by 12, you get something very close to 13, but not exactly 13. And that is because the mass of protons and neutrons are different. So this number is slightly higher than 13. Only carbon C12 is precisely 12 AMU. All other elements, all other atoms, have a number which is not exact in integer, slightly more or less. Okay, so now we are in a position actually to calculate the average atomic mass of carbon. How do you do that? You do it like this. You take the fraction of carbon C12, this is the abundance expressed in a fraction, times its mass, and you add the fraction times the mass of the other guy, which is carbon C13. But this is a weighted sum. This is the contribution of carbon C12. This is the contribution of carbon C13. The weighted sum is the average mass. It's 12.011. Put another one behind it. Okay? 12.011 is the average atomic mass of carbon. So the average atomic mass includes the weighted sum of all significant isotopes. Okay? Remember that. Okay, what is the average mass of other elements then? Well, let's have a look. Like I said, the mass of other atoms are determined as follows. You take the average mass of the element divided by the mass of carbon C12 and then multiply by 12 AMU. Again, the reason for that is that this unit here, this thing here, is relatively easily accessible experimentally. Okay, so what is the average mass of aluminum? Let's do that. The average mass of aluminum equals 2.248. What is this? Well, this is such a ratio determined from experiment. Okay? It's not an absolute number. It's a unitless number. It's a ratio between two experimentally accessible numbers times 12 AMU equals 26.98 senior. And that is exactly what you will find in the periodic table. Okay? 13 is the atomic number. It has 13 protons. Each aluminum atom has 13 protons. The average atomic mass equals 26.98. Question there.
You always use carbon for the...
Carbon is the reference. Yeah, another question.
But how would you find that number?
This number follows from experiment. You are not the one doing the experiment, so you don't know. But there are people that are doing this. Their jobs to do things like this, and they come up with these results. So we use them. Yes. This is okay. Okay. If your question is if you have to memorize a number like this, the answer is absolutely no. This is just to show you that this is the way we come to these numbers in the periodic table. Okay? What you should remember is that these numbers are all relative to carbon. That's the message. Okay? Okay, here it is, the periodic table, in all its splendid beauty. Okay, look at this. We'll actually dive in this somewhat more carefully in subsequent lectures. But you see those numbers here are now more familiar. They are the atomic numbers. They correspond to the number of protons. Okay? In this particular case, there's no atomic mass indicated. If you look at that one and that periodic table right there, you see the numbers below. In red are the masses, the average atomic masses. Okay, we'll talk more about the structure of the periodic table. Let me briefly end this lecture with kind of like giving you an appreciation of where the elements come from. Okay, so this is an interesting, striking statement. Approximately 73% of the mass of the visible universe as we know it is hydrogen. Okay? Hydrogen is the most abundant element everywhere. Okay? In our universe, in our reality, it is hydrogen. Helium makes up 25%. So you add these two numbers up, you're left at 2%. Everything else is 2%. Okay? 70% hydrogen, 25% helium, the two lightest elements constitute almost all the mass in the universe. All the other elements are a side note. Okay? Virtually all helium and hydrogen were formed during the first 3 minutes of the birth of the universe. This is how we understand how the universe is the way it is. Okay? So, that leaves us with the question, where do the other elements come from? It's kind of strange, because evidently we have many more elements. Okay, so they must come from combinations of helium and hydrogen. So this nuclear reaction is taking place that synthesize other elements that are heavy by combining lighter elements. Remember, the hydrogen atom only has one proton. If you smush two together, you have 2 protons. It means a heavier element. Okay? Helium has 2. So putting 2 hydrogen atoms together, you form helium. So if you put a helium and a hydrogen together, you have 3 protons, which is a lithium atom. So, basically combining atoms, fusing them, creating new nuclei with more protons and neutrons, is a way to synthesize new elements. And the way that happens, the way we understand it, is that it is stellar nucleosynthesis, which produces these heavier elements. Okay? You need very special conditions, very high temperatures, very high pressures to accomplish this kind of reaction. It doesn't take place all around us. You need very particular conditions, and they are obtained in the core of stars. This is where it takes place. Right? Now, interestingly, that is a process that can produce elements up to iron. Right? Beyond iron, this process cannot produce heavier elements. So iron would be the heaviest element. We know that there are heavier elements than iron. So where do they come from? The only way they can be brought into existence is through a supernova explosion. Okay? Again, the way we understand it is that the supernova explosion is the only natural process. There are other ways to do it. Actually, we can reproduce it on Earth in a nuclear reactor. Okay, so we can recreate conditions of supernova explosions. But without our own intervention, the only natural way in which this happens is through a supernova explosion. And that is pretty striking when you think about it. Because it leads to the following conclusion. All the gold and silver you're wearing, and even the calcium in your bones, come from a supernova explosion many eons ago. Okay? So, that's interesting. So the atoms that make up your body are very old. Okay? Very, very old. Especially the calcium ones and things like that. Heavy elements are old guys. Have been around for a long time. Long before you were here, they were there. They come from the stars. And this is basically what people say, we're made out of stardust. That is literally true. Literally true. We are made of the dust that's produced in supernova explosions. Okay, so look at this. Hydrogen, helium, the most abundant elements, then a big dip, and then all the other elements up to iron, another peak, and then beyond iron it goes down again. And it's really something we can explain now because of how easy it is to synthesize these things. Iron is very stable. To make elements beyond iron is more and more difficult. We need supernova explosions. Okay? Higher than 92, which is uranium, the nuclei are not stable. What does that mean? The nuclear force is not strong enough to keep these particles together. And that means that the particles tend to fall apart. That's called radioactivity. And here's kind of like the first radioactive elements beyond uranium are neptunium. Okay, so this is uranium, after Uranus, it's called uranium. Neptunium after Neptune, and plutonium after the planet Pluto. Okay, so these, Neptunium and Pluto, are the natural radioactive materials. Their nuclei are not stable. They tend to fall apart after a certain time. It's called the lifetime of the nucleus. So what is radioactivity? It's basically if you have plutonium nucleus, it doesn't live forever, it's unstable. It likes to emit an alpha particle, takes 4 particles out, 2 protons, 2 neutrons. If you take 2 protons out and 2 neutrons, you arrive actually at a uranium nucleus. But this is really a nuclear reaction, where one element is converted into another element. Okay? All right, that kind of concludes the basics of atoms, and we'll talk about it on Friday.